Whoa. Hey now.
Hey, we got some electric current here, and when we're going to talk about electric current, we're going to talk about the flow of electricity. So we've talked about magnets, how magnets help us make electricity, and that our electricity can make motion. Now we're going to say, okay, let's take this electricity and let's start making it look like the things we like to do. Electric current, it's the flow of charge, usually electrons. All right. Now, when we want electricity to flow, we have to find a material it likes to flow through. Those materials are called conductors. We talked about conductors with heat. We said, oh, things are conductors or insulators. We're going to use the same words. Conductors allow for the flow, in this case, not of heat, but of electricity. But very similar, conductors for electricity are also made out of metal. So metal is a good conductor, and things that aren't metal are good insulators. Fabric is an insulator. They used to wrap, before plastic was invented, they had electricity before they had plastic. How do you do that? How do you have a wire without plastic? They would wrap fabric around it. Cloth, nice thick cloth around it. Put cardboard around wires. All right, so insulators prevent electricity. Are conductors good or bad? Are insulators good or bad? It depends what you want to do. Do you want electricity to flow or not? If I have an electrical wire, I'm millimeters from death right now because I'm touching a wire, but the wire is surrounded by plastic. So the electricity can't get into my body because it can't get through that. So insulators are good, but we don't want everything to be insulators. Okay. And our body has wires in it too, nerves. It uses tissue and the flow of ions, and you'll learn about that in biology. But we have current too, and we need that current to flow. If a person has a spinal injury or a disease like multiple sclerosis, the current can't travel down the nerve. We need that flow to happen, that current to happen for the messages and the impulses to be received. Look at this, here's on a trampoline. Look at this, there's Heidi with her hair there. All right, so we can see that hair is standing on end. The charges are trying to get away from each other. So we talked about magnetic fields, but there's also things called electric fields. Electric fields. We're going to take a look at a video clip right here of this balloon being repelled by an electric field. Well, here we are. We got our Van de Graaff generator here. Let me turn it on. What goes on inside of this, it's a metal ball. And it's really simple, actually. There's a big rubber band that goes around and around. And it scuffs a carpet that's down inside here. That's like rubbing your feet on the carpet at a place with a carpet. And then it delivers the charge up to this ball up here. And then it gets trapped. It gets trapped up here because this is an insulator, this is a conductor. So let me turn that on. All right. Now at this point, there is a charge building up, and it wants to balance out somewhere else. So it zaps me. I have a balloon here. If I take this balloon, now it repels because as the balloon becomes the same charge, it gets pushed by the charges on there. There's no fan going on in there, but the balloon gets pushed away. That's pretty neat. So the balloon came back, didn't it? It came back because the balloon got the same charge as the Van de Graaff generator, and then it pushed, the two charges repelled and it pushed back. Some of them as well. Now watch this. I want you to kind of be thinking about this as I touch this. Now I can touch it. I want you to think about why. Now I'm going to hold that there. I'm going to take this here. Now I go. Oh, well, would you look at that? Now, look at that. The charge inside the ball now traveled throughout the entire, all the crepe paper there. And each piece wants to get away from the other piece. And so it's stretching away from each other. But it likes me because I'm a different charge, opposites attract. If I bring this guy back over, it goes down. I want you to think about why that is. All right, let me pull this guy off. Hey, now, I have all these hole punches in here. See those hole punches? From the copy machine. I'm going to put them on here. And guess what's going to happen? Guess what's going to happen? They're all going to become the same charge as this. Everything that touches becomes the same charge if it conducts electricity. This doesn't conduct electricity, so it just stays here. And now it's also going to go into those little hole punches. Let's see what happens. All right. Now, how do you get charged up on a trampoline? How do you get static electricity? Through friction. You're bouncing around on a piece of plastic. You're bouncing around. If you ever think about static electricity, there's always movement going on. There's always plastic involved. There's some insulator involved. Like a balloon. Movement on an insulator. Movement on an insulator. So when I have movement on an insulator, I get the charges stuck. See, static electricity is, these words don't go well together. This means static means to sit still, and electricity is moving. It's electricity that's stuck still. It's trying to walk across the balloon, but it's getting stuck. If I put a charge on here, the electrons want to get to the faucet. This electron right here I put on it wants to get to here, and it wants to get to the ground. It wants to get away from all the other ones, and it wants to get into the earth, into the literal ground. And so it wants to go through the pipes go into the ground, and it wants to walk down there. But it can't, because it's stuck on an insulator. Okay. So why do you get static electricity on your clothes? It's friction. You have movement. You have insulators. They get staticky. Even when you touch the clothes to a piece of metal, it's not like the electrons jump off. They're stuck on the clothes. It's like the clothes are like mud, and the electrons can't move their feet through the mud. They want to get away. They want to move. And if one sock's sticking to another sock, it means that one sock's positive and the other sock's negative. Conduction is when, kind of like when we talked about heat. It's when you have two things touch, and that's how conduction works with heat. You know, when the guy touches a frying pan, ow, I burned myself. All right, conduction for electricity is the same thing. When you touch, so when I zap somebody, because I got a charge, that's conduction. Zap. You know, when I was, what happened here? When I was a kid, we'd go to my grandma's place, and we would charge ourselves up on the carpet through friction, and then we would zap each other. I'm going to come back to that story in the future, but the charge wanted to get away from us onto another person. It wanted to spread itself out. So when I got near my brother, my charge spread out into his body and zapped him. Just like what you see here. She's charging herself up in this old car here. She scoots across. Because of the friction, she now has a charge that's not like his. She has a different charge as him because she charged herself up. That we would measure, we would call that a voltage. They have a difference. A voltage means difference. They have a difference. Here they're the same. Now she's different because she's been scooting, she's got friction. But what they don't realize is that they're about to spark because they're different. But once they kiss, now are they still different? They got zapped. But now they're not different anymore. Now they're the same. They have the same charge because her charge traveled into him. If they kiss for a second kiss, will they zap a second time? No. Because they're now the same. She'd have to go recharge herself. So once the discharges happen, then there's no second shock. Induction is when you produce charge without touch. Here we have, I kind of did this with that flask here. I did put it away. It's on my desk, somewhere. It doesn't matter. When you can charge something without touching. Here we have two metal spheres here. We know they're the same charge because they're touching. He brings this rod down. The charge is negatively charged. all the negatives that were here run over to here. They want to get away from here. They run over. If he pulled this away, they'd run back. Well, let's spread out again. Oh, let's run away. Now, instead of pulling it back, he now pushes this guy away. Now they're stuck on an island over here. He pulls this away, they want to come back over here. I want to come back. But they're separated. His is charged up. He charged it up without ever touching anything to it. He just got close to it. And that was induction. Your toothbrush works, your electric toothbrush works this way. No metal touches with your electric toothbrush. It's all plastic parts, even on the bottom where it plugs in. It's all plastic. It charges this stuff up without induction. So there's like an electric toothbrush there. So what I want to do is I want to take a moment here and I want to look at this demonstration that I just did with my family here with the Van de Graaff generator. All right? Now, put my hand on here. Ooh. Now, I can feel some stuff happening. I can feel my clothes kind of sticking to me. In a second, here we go. Why don't you try this in my fingers? Can you hear that? I'm going to need to bring Heidi. Why don't you come over here? This is Heidi, my daughter. You know her? I love her so much.
That hurt.
Whoops. I didn't know that was going to happen. Now you hear my fingers? Unlimited power. Okay, Heidi, come and touch my finger. See if it shows up in the camera. Did you see that?
Yep.
Okay, come over on the other side, Heidi.
Do this again.
Watch this. Purple. We'll act differently. Now we would have brought, oh, you hear that hand?
I have the power.
Give it a shake like that, just side to side. So what's happening is that all the hair, Sam's becoming the same charge as the bulb. And so her hair doesn't like her other hair because it's all the same charge. Now why doesn't the charge just go down into the floor? Because she's standing on a crate. So the charge has no way to get to the earth. It's staying on her. Now, well, let's pause here for a second and say, why does this, what does this do though? We've been doing this and it makes everything safe. It now makes there be only one path, well there's two paths to the earth. It can go through Sam and get trapped, or it can go through this metal, to this metal, to this metal, to the pipes which go to the earth. So I gave it, the electricity, two choices. Go through Sam and her shoes and the plastic, or go through the metal. And it made a decision. It chose to take the path of least resistance through the metal. Meaning Sam gets a day off. She gets a break. She's no longer an electricity highway. It goes through here. So you can step off now. And now we gave it a choice. And it chose this path. If I remove this, now it only has one path. It has no path at the moment. But when I come along, it now picks me. And now it chose me to go through to the floor. Still had to slow down as it went through my shoes. It slowed down to go through my shoes. And I'm glad it slowed down. So now what we're going to do is this. I'm going to hold Sammy's hand because she's my favorite. Okay, Heidi, go ahead and touch the ball, or get close to it at least. I didn't feel anything.
Stop, don't do it again.
Do it again.
No.
She's feeling it. Why am I not feeling it as much? Heidi feels it perhaps the most, then her, Sam second, and then me not at all. It's making trips to the ground. It's choosing to go through Heidi first, and then wants to get to, it doesn't want to hurt us. It just wants to get to the ground. So it goes through Heidi's shoes. And Heidi might have thick shoes on. So Sam might have thinner shoes on, and so maybe it's going through Sam more, because she's the better path. All right. Now, let's try this. It's having to go through shoes. Shoes slow it down. I'm going to give it another choice. It can go through our shoes to the ground, or it can go through the pipe to the ground. So will it go through our hands to the ground, or through our feet to the ground? Go ahead, Heidi. Touch the ball.
Ow, ow, that hurt. Don't do it. No.
Now I feel it.
No, stop.
It's actually going through me now because I'm a more important part of the path. My shoes aren't really the issue. It's now saying I can go through the pipe, through the hands. Go ahead. Heidi, one more time.
No.
I feel it in my hand. I don't feel it in my feet. I feel it in my hand. Now if I let go and Heidi does it, go ahead, Heidi. Sam feels it in her feet now more than her hands, I imagine.
Nope.
Where do you feel it? She feels it in her arm, but it's going through her arm to her feet instead of through her arms, through my arms to here. Go ahead, Heidi, do it again. I feel it in my wrist. It's more fun to do with 25 students and have them all scream at the same time. It's the same voltage. We're not changing the voltage. But what we did was by making ourselves being better conductors, we changed the current. This thing's called the executioner. Heidi, come here.
Don't touch me with that.
Just put your...
Doesn't it hurt?
No. Put your finger out.
I don't want to.
Here. Come on, it doesn't hurt. Here, come try it.
I can feel it here.
Be on the camera. Come on. This is your moment.
It hurts.
Oh, of course not. See, it doesn't hurt. Put it on. All right, go ahead. Let's ET this thing. Put your finger out.
I don't know how to do
Sam,
it.
it's fine. Touch it.
All right, well, how neat was that? Okay, so let's look at lightning. See, so now that we saw that stuff. With lightning, the bottom of the clouds, we got motion again. We got water, which is an insulator, and especially fresh water. And as it's tossing around in the wind and updrafts and sideways winds, you end up with like a staticky situation where you end up with the clouds getting charged up. And then what happens is the charge up here is different from the ground, and the lightning can zap down, or it can zap up. Ultimately, what you want to do with lightning is make lightning not like you. How do you make lightning not like you? Be wearing shoes. Make sure there's something more desirable to strike than you. Bring a tall friend with you. Get low into a ditch. It wants to get to the earth. Don't be part of the earth. Let the earth be lower than the earth. Get into a ditch. If it's going to strike a tree, well, don't get under the tree. It's going to start to it could be off a little bit. But do you want to be the tallest thing in the field yourself? No. So you're kind of in a trap there. But that's where the ditch comes in. And if there is no ditch, well, keep your shoes on, obviously, and squat down low. Squat down low. If you're on top of Half Dome, for instance, you wouldn't want to be standing on top. You want to be low. But don't put your hand down on the ground. Put your hand down on the ground, your hand's not wearing a shoe. The electricity will have a choice. Do I want to go through two shoes or the hand? They'll say, I'll go through the hand. All right, well now it's going through your hand. Better it goes through the shoes. The shoes will slow it down. It won't hurt as much if it slows down. You give it a fast path through your hand with no shoe, it's going to choose that path and hurt more. You don't want it to go through your brain. So, if you, or your heart. If I had a choice in a thunderstorm to lift my left arm or my right arm, if my heart's on this side, I don't want to lift any arm, but this arm would be smarter because it'll go down this side of my body and I'd have my this foot up and this hand up. It would go through here. Lightning enters your body through one spot and exits through another. You can tell by the burn spots with lightning. So, it entered a person could tell you, it entered through my shoulder and exited through my foot, my left foot, or whatever. But if you take off your shoes, it's going to go even faster through those same parts. It'll hurt even more. With that Van de Graaff generator, it was the same voltage every single time. It was the same voltage. But we were, by grabbing pipes and so forth, we were making it have an easier path. It was pushing through us, but it was able to push through us faster because we gave it a cleaner path with no shoes. Okay, so that's lightning. We could have said more about it, but that's fine enough for now.